Okay, welcome back. So last week we started discussing transition kernels. Just as a recall, what is a transition kernel? It is a bridge between two measurable spaces in some sense. So let's say you have two measurable spaces, E and G. A transition kernel is a function of two variables. The first variable is a point in the first space, and the second variable is a set, a measurable set, in the second space. So when we talk about a transition kernel, it is a function from E cross script G to R bar plus. So this is a transition kernel if, as a function of f, this is a measure, on G, for fixed x, of course. And as a function of x, this is a measurable function, or a random variable is a measurable function with respect to, of course, script E, right? Script E. And here we have the Borel sigma algebra for fixed set f in the second space. So you can use it as a measure if you fix the first variable. You can use it as a random variable if you fix the second variable. And indeed, you can do integration with that. So if you have a measurable function on the second space, you can use this as a measure for fixed x. So this becomes an integral over G. So now what is this? This is a function of x. And indeed, last time we showed this is a measurable function of x. So this is what we call kg of x. Okay? Although g is a function on the second space, this kg makes it a function on the first space. And if you have a measure on the first space, you can use the function part of k for some fixed f and integrate it with respect to this measure. So now this is an integral on E. So you can use k as a measure or as a measurable function whose integral you can evaluate with respect to some other measure. So now what is this? This is a function of f, right? This is a function of f. So we write nu k at f. This is for x in E, and this is for f in G. Indeed, we also showed last time that you can do both, because now kg, so some facts from last time, some facts. So kg is measurable if G is measurable. But kg is on E, whereas G is on G. This is on the first space, this is on the second space. And nu k is a measure if nu is a measure. Okay? But we have to tell the spaces. So this is measurable with respect to script E, whereas this is measurability with respect to script G. This is a measure on the second space, whereas this is a measure on the first space. So it changes the space when you do this operation. And indeed, you can do both of them. So you can use kg as a measurable function on the first space and integrate this with respect to nu. Or you can use nu k as a measure and integrate g with respect to that measure. So by this, I mean what? I mean an integral of kg with respect to nu. And this definition of kg is just this, g of y kx dy on one hand. And on the other hand, we have the integral of g with respect to nu k. So what is nu k? Well, let's write nu k dx, dy. And we have that nu k is defined over there. So sometimes we may even write it as, so we can write this nu k dy as kx dy nu dx. But since I take the integral over the first space, now this is like a differential form with this dy, right? This is this is the meaning of nu k dy. So I use this as the nu k and integrate g with respect to this measure on the second space. Okay? So this is my measure part. And they give you the same answer. Okay? They give you the same answer. This is our claim. Okay? So 1, 2, 3. This was a theorem that we stated and proved last time. And indeed, we don't have to stop at this point. We can even use k, the measure part of k, not just to integrate functions on the second space, but also functions on the product space. We're going to use k to integrate a function on the product space. And this way, for instance, if we integrate indicators of measurable sets of this product space, we're going to get a measure on the product space. So the title is the product of a kernel and a measure. Product of a kernel and a measure. That's going to give us a very nice result, a way to create measures on the product space using a measure on the first space. So let me write be a measure space. Let G be a measurable space. And let K be a transition kernel from the first space into the second. And we assume K is sigma finite. So here comes the theorem. I'm going to state the A part later. First, I'm going to write down what we have in the B and C parts. And it's going to be clear what we should have in the A part. Okay? So here's part B of this theorem. So I'd like to define a measure on the product space. So I'd like to tell you what the value of my measure is at every measurable space. Not just measurable rectangles, but also other sets that are in this product sigma algebra. here's how I achieve a measure on the product space. I look at the indicator function of this set, which is a function of x and y on the product space. I'm going to integrate this using k, so that now this is a function of x. K is used to integrate indicator A. So now y is killed because we took an integral. We evaluated an integral over the second space. So now it's a function of x. Therefore, I use my measure on the first space to integrate this function over the first space. Okay? So okay? Then pi is a measure on the product space. And we even have the integral of a function with respect to pi given by the same formula, the same definition. F, so now indicator is replaced with an arbitrary measurable function, let's say positive, for every f from the product space into the positives that is measurable. So for this, we write, so in short, we write pi dx dy is nu dx kx dy, or pi is the product of nu and k. Okay. So what is the problem here? What is the problem here? So note that this integral is not one of the integrals that we looked at in this board, because here we used k only to integrate a function of the second variable, not a function of two variables. Okay? So that raises the question of measurability of this form. So we have to make sure this integral is well-defined first, and then this is also a measurable function of x, so that we can use it as an integrand of this measure nu. So this forms part A for a measurable function f on the product space. I'm going to say it not only for indicators, but also for general functions, because we also need the integral of f with respect to k, right? So for a measurable function f, this kf of x is well-defined in R bar plus for each x. Moreover, kf, which is defined on E to R bar plus, is a measurable function. Measurable function. Okay? So we only have part A for technical reasons, okay? To have a function that is measurable so that we can use it as an integrand with respect to the first measure. So therefore, I'm going to leave it as a homework problem. So this is a homework problem. And there are some details. There is some guidance, okay? You first need to assume K is a finite kernel, and then you have some proof, etc., etc. So there is parts A, B, C, D, etc. So this is homework 5 question, homework 6 question. But it's not a very interesting result, right? It's just measurability, just checking that Kf is measurable. What is more interesting is to use it here as an integrand. So we're going to prove part B. But there is also part C. Let me also state this. So assume K is sigma bounded and nu is sigma finite. Then pi is the unique and sigma finite measure on E cross G such that pi of a measurable rectangle. So I'm specializing into measurable rectangles now. So let's evaluate this integral for a measurable rectangle. So if I have a measurable rectangle, so it's going to be indicator of D of x times indicator of f at y, right? So this is going to be D of x f of y So what is the value of this? Well, first of all, this does not depend on, so this part does not depend on y, so I can take it out. And now what is the value of this integral? Well, for fixed x, this is just the integral of a measurable function, right? Integral of the indicator of a measurable function. So it's going to give us x of f. So now this is nu dx. So I can also write it as the integral over d of this form for every d in script e and f in script g. So that's the unique measure which gives you those values on measurable rectangles. Since pi is now sigma finite, so pi is sigma finite now, its values are uniquely determined on measurable rectangles, right? If you know the values, the measure is uniquely determined by those values because of the uniqueness result about measures, right? So measures are uniquely specified by their values on a pi system if that measure is finite or sigma finite. So in this is the sigma finite case. So now this is like a main result, and we're going to specialize into, we're going to look at the special case of this theorem later once we prove it. And that's going to give us Fubini's theorem. So the theorem that I advertised last Friday. Okay, so let's try to prove this theorem, parts B and C. Okay, what do we have to show? We have to show that pi is a measure. Okay? Well, first we have to make sure pi a is well defined. This is a valid thing. But this is thanks to part A, which tells us that kf, or k indicator a, is a measurable function of the first variable. So there is no issue about the well-definedness of pi. Let me write proof of B. Okay. So first, pi of a is well-defined. for each A thanks to part A. Next, we show it is a measure. We show pi is a measure. So if you look at pi of empty set, so this is indicator of empty set xy, kx dy, nu dx. What is indicator of empty set? What is indicator of empty set? Okay, you should, yeah? So integral of 0 is 0. So this is 0. Integral of this is 0. Integral of another 0 is 0. So this is 0. Okay? Now what is the other property that we have to check in the definition of a measure? What is the other property in the definition of, sorry?
Additivity of disjoint sets?
Yeah, countable additivity, we call it, right? So to show countable additivity, let A1, A2, etc. be measurable sets that are disjoint. So I'd like to be able to use monotone convergence theorem, okay? So to prove that pi of the union is equal to the sum of the pi's of AIs, I'd like to use monotone convergence theorem, but with those sets I cannot use monotone convergence theorem because they are just disjoint sets. But we all know by now that whenever we have disjoint sets, we can always create an increasing family of sets, and their indicators are going to form a family, an increasing sequence of functions, right? And the limit of the indicators is going to be the indicator of the union of everything, right? So now this should be well known to all of you, and if not, you should revise your notes on these things in the first chapters, first 2 chapters maybe, okay? So if I have A1, A2, etc., let us also introduce Bn for every n. So indicator of B1 is less than indicator of B2, etc., etc., and the limit is indicator of the union of everything, which is also the indicator of the union of Bn's. Okay, so this is a sequence of functions satisfying the assumptions of monotone convergence theorem. Okay, so but why are we gonna use it? So let's look at pi of the union. Okay. So what is that? It is indicator of the union K nu. Okay. Now what is indicator of the union? It is the limit of indicators of Bn's, because we created those sets and they increase to the indicator of the union. So using monotone convergence theorem, I can take this limit outside the integral and get this. But at the end of the day, I want to get sum of pi ai's, right? So in my end result, I don't really want bn's. So let's use the fact that bn is a disjoint union of a1 to an. So let me also say here that indicator of bn is nothing but indicator of a1 to indicator of an. So I can see it as sum of indicators of ai's. So integral of a finite sum is equal to the finite sum of integrals due to which property of integral? Integral of a finite sum is equal to finite sum of individual integrals. Simply linearity, right? And everything is positive. There is nothing about infinity minus infinity, etc. So this is lim n goes to infinity sum of integrals, okay, x dy nu dx. So, okay, I guess that's the right way to put the parentheses. Okay, so now what is this? Limit n goes to infinity, I1 to n. What do we call it? Limit n goes to infinity, I from 1 to n. It's a series from I1 to infinity, right? Just I1 to infinity. So this is the definition of an infinite sum, right? So now I have integral of an infinite sum, and the integrands are all positive. Which theorem can I use to swap the order of this integral and the infinite sum? Exactly, Mon series. We used it last time as well, right? Okay, so we use Mon series, the series form of monotone convergence theorem, to get this is equal to I from 1 to infinity, E over G, AI, x, y, k, x dy, nu dx. And this is what we wanted. This is what we wanted, because this is exactly pi of AI by definition. So we showed pi is a measure. Yes?
We need some verification before using the Mon second time, because now our monotone convergence theorem refers for a different type of functions, I think.
Here, right?
Yes, the second one is not referring to simply.
No, it's just referring to those functions, right?
Yes.
And for them, no monotonicity is required. The series form of monotone convergence theorem actually doesn't have any monotonicity in it. Monotonicity comes from the fact that you're looking at 1 to n, 1 to n plus 1, 1 to n plus 2, and if you have positive terms, they form an increasing sequence. Okay? So this name, monotone convergence theorem series form, only tells you how to prove this theorem, this swap, right? Using monotone convergence theorem. But there is no monotonicity in it. So just positivity is enough. These are just positive measurable things, so it's fine. Okay. Well, how to pass to pi a to pi f? How to pass from the indicators, from indicators to general measurable functions? Well, to show the formula for pi f, extend the formula for pi a, which is nothing but pi indicator a, to simple positive functions using linearity, and then to positive measurable functions using monotone convergence theorem. I leave the details for you. In fact, we did it for just one measure, right? If you have a definition of a measure, you also know how to integrate functions with respect to that measure, right? Simply take a simple positive function, and then use the fact that this is nothing but pi of indicator A, right? So if you need to integrate not an indicator but a simple positive function, you know how to get your result using linearity. And if you have simple positive functions and you want to pass to general positive measurable functions, you can use monotone convergence theorem by taking a sequence, increasing sequence of simple positive functions. So I leave this part as an exercise. But the hard part was to show that pi is a measure. Okay? And what else do we have here? Well, nothing, right? In short, we write this and that, etc., just notation. So let's pass to part C. But before that, any questions about part B? Any questions about part B? You have some missing part? So to show the formula for pi f, extend the formula for pi a equals pi indicator a, two simple positive functions using linearity, and then two positive measurable functions using monotone convergence theorem. Maybe too many abbreviations in one sentence. So let's show part C. What does part C say? Well, we need to assume K is sigma bounded and nu is sigma finite. Then pi is the unique sigma finite measure. Let's first show that pi is sigma finite if we assume K is sigma bounded and nu is sigma finite. That was the end for part B. Okay, so proof of C. So we assume K is sigma bounded and nu is sigma finite. I'm going to recall what sigma bounded is. Anyway, let's show pi is sigma finite. So K is sigma bounded means there is a measurable partition G1, G2, etc. of G such that the kernel is bounded over each of the sets in the partition for all I. And nu is sigma finite means there is a measurable partition, let me call it E1, E2, etc., such that of E such that nu of EI is finite for all I. I should have said J here, for all I. So we have our product space. Let me not draw it this way. So let's say this is E and this is G, okay? So you have a grid for E like this. So E1, E2, E3, okay? And you have another grid for G. So G1, G2, G3, etc. Vertical and horizontal ones. So this gives me rectangles, right? So E4 cross G3. So I can look at sets of the form EI cross GJ those rectangles form also a countable family, right? You can count them as 1, 2, 3, 4, 5, 6, 7, etc., etc. And they are measurable sets because they are measurable rectangles. And they partition E cross G. So they form a measurable partition of E cross G. So all I have to do is to check that pi is finite on each of those sets. So pi of EI cross GJ. What is that? Well, it is indicator of EI of X, indicator of GJ of Y. This is the indicator of EI cross GJ, right? So integrate this with respect to K, integrate it with respect to nu. So now what is that? Well, this is EI of X and K X of GJ nu dx, or EI GJ nu dx. So we have to argue that this is a finite number. This is a finite number. Well, this is bounded by some finite number, right? So I can bound this by its supremum over X, so that this is less equal supremum of kxgj, which is a constant now. It does not depend on X, right? I bound it by a finite number, times the integral of nu dx EI, which is nothing but nu EI. So this is finite. This is finite. Therefore, this product is finite. So pi is sigma finite. Sigma finite. And we also need to say that it is the unique measure which assigns some values on measurable rectangles. But this is now, this is just going to follow from the uniqueness result about measures. So if pi tilde is another measure that agrees with pi on measurable rectangles, then we also have pi tilde of EI cross GJ is equal to pi EI cross GJ for all ij, because if they agree on measurable rectangles, they also agree on those special measurable rectangles, because that is the assumption. This is also finite, okay? This is finite. So this was the assumption in the theorem about the uniqueness of sigma finite measures. So that theorem had part A and part B. Part A is just about finite measures, for instance, probability measures, and part B is about sigma finite measures. And on that, you need to have that they agree on a pi system, and moreover, they have to agree on the sets forming your measurable partition. Okay? So by the theorem on uniqueness of measures, we must have pi equals pi tilde. This shows the uniqueness of pi. So this is about the product of a kernel and the measure. Okay. So now we're going to look at the product of two measures. One on one space, another on the other space. Product of two measures. It's going to be a special case of the theorem, the previous section we looked at, but we're going to have some more result. Okay? So let's say we have B. So I don't have a kernel, okay? B2, let's say, sigma finite measure spaces. Now, how can I embed this setting into the setting of the previous theorem, where I had a measure on the first space that is common, but now I don't have a kernel from the first space to the second, but I only have a measure on the second space. So how can I see this as a kernel from this to this, from the first space to the second? How can you see a measure on the second space as a kernel from the first space to the second? What can you do? How can you see it as a kernel? As a trivial kernel, not a true kernel. So what is a kernel? Kernel is both a function and a measure. So now I just have a measure, no function part. But you know, constant functions are also functions, right? So letting kx of f to be lambda of f for all x and f, we may see lambda as a kernel k from E into G. So we may define the product of nu and lambda by this formula. This formula. So I'm just going to write lambda here, lambda dy. Pi of A is indicator A xy, lambda dy, nu dx, second space, first space, for all A in the product sigma algebra. So in short, we write pi dx dy equals nu dx lambda dy, or pi is just nu cross lambda. Okay? Let me write it as a theorem, because we're not just going to write down a corollary to this theorem, but also the theorem is going to have a new claim. What is the new claim? The new claim is that this is a symmetric picture in some sense, right? I have measure on both spaces. It's not like I have a measure on the first space and a transition kernel between the two. It's a fair situation. Both spaces have their own measures. So if I can define pi as an integral on the first space of an integral on the second space, I would hope that I can switch the order of integration and also write it as an integral on the second space, where inside I have an integral on the first space. So I should be able to swap the order. This is what Fubini's theorem says. Okay? So let pi be defined by star. What is star? It is this star, right? So pi is the unique sigma finite measure on E script G such that pi of D cross F is pi nu of D times lambda of F for all D in script E and F in script G. We have, let me say it this way. So part A, okay, this is Fubini's theorem. So for every f that is positive and measurable, we have pi f, which is by definition f with respect to pi on the product space, can be calculated in two ways. One way is to rewrite this formula using f. The other is the reverse order. Part B is called Pinellas Theorem. And this deals with functions that are not necessarily positive. Okay? So since we usually deal with positive measurable functions, Fubini's theorem is usually okay enough. But sometimes we have to deal with functions like cosine, sine, etc. So we need to deal with functions that can also take negative values. So we need a second part, which is about when we can do this swap for functions that can also take negative values. So if f now into reals, or maybe just r bar, let's say, is pi integrable, meaning that this pi f is well defined. So let me write it this way. Pi f plus is finite, and pi f minus is finite. Then what do we have? Well, the section of f is lambda integrable for nu almost everywhere, for nu almost every x in E, and, or let me say it this way, okay? So the section of a function is what? You freeze the first variable and see it as a function of y. So this is lambda integrable because lambda is the measure on the second space. So the section in the second variable is nu integrable for lambda almost every y0 in G. And we still have the swap, let me call it double star. So in other words, if your functions are integrable but can take negative values, you can still do the swap of the order of integration. Oh, I have to stop. Let's do the proof in the second hour, okay?